Good morning everyone. This is the last lecture of Lagrange's equation. I recommend you to please use earphone if the audio of this lecture is very low. In this lecture we are taking two questions of final year exam which are asked in Lalit Narayan Mithila University in the year 2017. First question is the Lagrange's equation, Lagrange's partial differential equation, which is basically in the form P, capital P into small p plus capital Q into small q equal to R. If you compare this equation with the standard form, then you will find that the value of capital P is mz minus ny, the value of capital Q is nx minus lz, and the value of capital R is ly minus mx. So if you have not watched the previous videos, then I recommend you to first watch those videos so that you can completely understand what is Lagrange's equation, what is the standard form of Lagrange's equation, what are the simultaneous differential equations, how to find the integrals of simultaneous differential equations, and how to solve the Lagrange's equation of the type capital P into small p plus capital Q into small q equal to R with the help of simultaneous differential equations. So let us start the solution of this question. We have already seen how to write the auxiliary equations of the Lagrange's equation. It means that we start solving this equation with the auxiliary equation. So how you write the auxiliary equation of a Lagrange's equation? You write dx by coefficient of small p equal to dy by coefficient of small q equal to dz by coefficient of not coefficient, the term which is in the right side of this equation. So the auxiliary equation is here dx by mz minus ny equal to dy by nx minus lz equal to dz by ly minus mx. Now if you take the multipliers L, M and N, then we obtain that these three fractions equal to this one. So how you get this fraction? You get this fraction by multiplying L by dx plus M into dy plus N into dz divided by L into mz minus ny plus M into nx minus lz plus N into ly minus mx. Okay, we have already also seen the lecture. The name of the lecture was Prerequisite to Simultaneous Differential Equation, or in the first lecture of Lagrange's equation. Somehow I am not remembering in which lecture we have discussed thoroughly that how you write this fraction. Okay, so go to the previous lectures, you will completely understand it. So here you can see that when you are taking L, M and N as multipliers, then you can write this three fractions equal to this one. Now here it is plus of LMZ, and here it is minus of LMZ, and it is minus of LNY, and it is plus of LNY, and here it is plus of MNX, and it is minus of MNX. So after calculating this fraction will be equal to LDX plus MDY plus NDZ divided by 0. Okay, so after calculation you are getting the last fraction equal to this one. So denominator of this fraction is 0, so numerator of this fraction will also be 0. So it will become LDX plus MDY plus NDZ equal to 0. After integrating this equation, you will get LX plus My plus Nz equal to integrating constant. So this is the first integral of the auxiliary equation of the Lagrange's equation. Okay, so remember this equation. This will help you to write the solution of our given Lagrange's equation. Now again if you take x, y and z as multipliers, then you can write these three fractions equal to this one. Here we have done the similar calculation. We have multiplied x by dx, y by dy and z by dz, and then we have added all these three things, and similarly we have multiplied x by this term, y by this term and z by this term, and we have then added all these three things and we get this fraction. Here also you can see that after calculation this denominator becomes 0, because here it is m of plus of mxz and here it is minus of mxz. Here it is minus of nxy, here plus of nxy, and here it is minus of lyz and here it is plus of lyz. So after calculation you are getting this fraction whose denominator is 0, so its numerator will also be 0. Therefore we are getting x dx plus y dy plus z dz equal to 0. Now upon integrating you will get x square by 2 plus y square by 2 plus z square by 2 equal to integrating constant. So here we have this equation after integration of this the above equation. Now taking this 2 to the right hand side, you will get this one, which is x square plus y square plus z square equal to 2b dash, and this 2b dash we write here equal to b. So this is the second integral of the auxiliary equation, and you remember that the first integral of the auxiliary equation which we have written in the equation 3, that lx plus my plus nz equal to 0, and this is the second integral. So we can write our required Lagrange's equation as phi of x square plus y square plus z square comma lx plus my plus nz equal to 0. So we are writing this one. So here you can see the first integral, this one the first integral which we have used, this one lx plus my plus nz, and the second integral is x square plus y square plus z square. So using the both integrals we can write this our required solution as phi of x square plus m square plus z square comma lx plus my plus nz equal to 0. Now come to the next question. This question is also in the form of Lagrange's equation. The auxiliary equation of this equation can be written as dx by coefficient of p small p equal to dy by coefficient of small q and equal to dz by the term which is right in the right side of the equation 5. So our auxiliary equation is like this. Now taking first two fractions you will get this equation, and after cross multiplication you will get x square dy dx equal to y square dy. Okay, now integrate this equation, you will get x cube by 3 equal to y cube by 3 plus integrating constant, and when you take y cube by 3 to the left hand side you will get this one, and this a dash is the integrating constant. Now take 3 to the right hand side, you will get x cube minus y cube equal to 3 a dash equal to a. This is the first integral of the auxiliary equation. Remember this equation which we will use in writing the general solution of the Lagrange's equation. Now taking the last two fractions of 6, okay, this is the auxiliary equation, our auxiliary equation. Now we are taking the last two fraction which are dy by x square equal to dz by x square into y square into z square. Okay, so taking the last two fractions of the equation 6, we are getting dy by x square equal to dz by x square into y square into z square. Now here you can cancel this x square, so cancel it, and then you will get, and take this y square to the left hand side, you will get y square dy equal to dz by z square. Okay, which upon integration you will get y cube by 3 equal to minus of 1 by z plus integrating constant, and when you will take the minus of 1 by j to the left hand side, you will get this equation. So this is the second integral of the auxiliary equation, and the first integral of the auxiliary equation, which is given in equation 7, which you can remember this one, it is x cube minus y cube, and the second integral is y cube by 3 plus 1 by z. So our solution can be written like this: phi of x cube minus y cube comma y cube by 3 plus 1 by z equal to 0. So this was the last lecture of Lagrange's equation. In the next lecture, we'll start Charpit's equation. We'll see that what is Charpit's equation. It's a kind of partial differential equation, and then we'll see how to solve Charpit's equation. Just similar to the Lagrange's equation, we'll see that how we write the auxiliary equation of the Charpit's equation and how we solve that equation. Okay, thank you.